Dear students, Assalamu alaikum, and welcome to our 16th program on Software Engineering 1 course. In the last two programs, we discussed some basic concepts related to software design. I would like to stress that software design is a bridge between analysis and implementation. That is, once we know the user requirements, we need to design the system before it can be implemented. The major design activities that are carried out during the design are shown in this diagram. So during the design, we do the data design, architectural design, interface design, and procedural design. You would like to notice one thing here, that all these designs are obtained from various analysis models that we prepare during the analysis phase. Our today's program will focus on data design and software architecture design. Let's start with data design. During data design, we refine the data models prepared during the analysis phase into implementation-specific representations that can be implemented and processed by a computer. During data design, depending on the nature of software or application you are building, in the data design phase, we design the database architecture and the data structures. You need to design database or data structure or both, depending on, of course, the type of application you are building. It is quite straightforward to transform your ER data model that you produced in the analysis phase into a data model such as a relational model that can be then directly implemented as tables or relations with a relational database package. Of course, if you are using some other kinds of database packages, then the design should map the ER model into that specific data model, such as object-oriented data model, network, or hierarchical data models. Here is an example where we map an ER diagram into relations or tables that can be implemented using a relational database package such as Oracle. So we take a very simple ER diagram as shown in this diagram. We have only three entities: teacher, students, and courses, and some of the relationships are also shown in this diagram. Now, we have very elaborate methods which can be used to transform or map the ER diagram into data model. We used one such method to obtain these tables from the ER diagram. You must note one thing important here in the design, that we basically identified different table names and the attributes which we would like to store in each table, their type, and certain constraints which the table or the attribute must satisfy. So we obtain all these tables from that ER diagram. Of course, this database design is not complete in many respects. For example, we have omitted the detail about many tables, and a lot of constraints have not been specified here. But while you are doing the data design, it is important that you must include all the details which are necessary for the implementation. For example, you should specify the internal schema, for example, how these tables should be physically stored on the disk, and all other constraints which should be specified so that the implementer can implement the tables directly into a database package. Also note that information that we use in the data design come from the data model and data description that we prepare during the analysis phase. Now it is important that once you are doing the design, you should not be including any extra information which is not present in your analysis models. Now, if you come across a situation where you think that some extra information needs to be added during the design phase, that implies only one thing, that your analysis is not complete in some respect. So you should go back to the analysis, improve your analysis, include the missing details, and then come back to the design phase. At the component level, you might need to design the specific data structures that will be processed by that component. For example, if you are writing a CPU scheduler for an operating system, which selects a ready process for dispatch to the CPU, you might need to store the PCB or process control block of the processes you want to schedule in a linked list queue, or in a priority queue, or in a number of queues, depending on the algorithm you choose to implement. For example, if you are implementing first come, first served scheduling algorithm, a linked list queue might be a suitable data structure to be used as shown in this diagram. So this data structure, which defines the structure of the PCB, which includes the process ID and the process parent ID and the other details depending on the operating system. And this is the data structure we define as the struct in C language, and this is the graphical representation of the data structure. So we need to store the head pointer, which points to the first process in the queue, and of course, it is linked to the PCB of the process. Now, while designing the data structure, you should consider what operations are to be performed on the data and how they will be implemented, and then select a data representation that is most efficient for that type of processing. A more detailed discussion on data design can be found in your courses on data structures and database management systems. You should remember that during the data design, we not only design the database as is generally believed, but we also design the data structure which will be processed by the application we are going to develop. The second type of design model that is prepared during design engineering is called the architectural design. Architecture design of a system is concerned with identifying components and their properties and how the components would interact with each other. So basically, during the architecture design, you specify the components or the module which make up the whole system. You identify what functions will be performed by each component, or what functionality will be provided by each component of the system. You should also mention the way these components will interact with each other to achieve the overall performance and the functionality of the software. Architecture design of a software is equivalent to the floor plan of a house, which depicts overall layout of the rooms, their sizes, shapes, and relationship to one another, and the doors and the windows that allow movement into and out of the rooms. That is, it gives an overall view of the house as shown in this diagram. So this is a floor plan of a house. So we show where different rooms and kitchens, doors and windows will be, and how the movement of the people will be from one room to another room. For example, where is the location of the doors and the windows and all other things. So once you have the architectural design of a house, of course, now it's quite straightforward to build a house according to that design. In a similar way, The architecture design of a software is a representation that enables a software engineer to analyze the effectiveness of the design in meeting its stated requirements and analyze the alternatives at a stage when making design changes is still relatively easy. Architecture design is also important for reasons such as it may be used as a focus of discussion by system stakeholders, and it may be reusable across a range of systems. I would like to emphasize the point here that you should not start developing the software unless you have done the design of the software. I have seen many students basically starting their work with the implementation. They straight away go to the implementation and then they do the design while they are doing the implementation. Of course, this technique can be used if you are working on a small system. But for large system, you will not be able to get a quality software. So keep that thing in your mind, that to develop a high quality software, you should start by analysis, do the design of each and every component you are going to develop, and then do the implementation. Of course, some prototyping might be used, but that prototype should not be taken as the final product. Dear students, the architecture of software affects the performance, of course, its robustness and maintainability of the software. Therefore, particular styles and structures chosen for application not only depend on the functional requirements of the system, but also on the non-functional requirement of the systems. The point is that while you are doing the architecture design, you should not only consider the functional requirements of the system, but you should also look for the non-functional requirements of your system. Software architecture design is a complex undertaking and requires special knowledge, skills, and creativity. Software engineers have proposed a number of architecture styles for different types of systems, which provide us with a framework or template that we can use as an aid to design our system. An awareness of these styles can simplify the problem of designing system architecture. But bear in mind that most large-scale systems are heterogeneous and they do not follow a single architecture style. Therefore, while you are doing the design, you should be looking for what's available, what designs are available, and you might need to customize those architecture design according to your own requirements. But still, familiarity with the common architecture design is a very helpful thing to do your own design. The most commonly used architecture styles are data-centric architecture, client-server architecture, data flow architecture, layered architecture, call and return architecture, and object-oriented architecture. We'll briefly discuss some of these styles. Of course, you can see more details in your textbook. The first style we are going to discuss is called the data-centric architecture or repository model. In the repository model, in the center, we have a data store, a repository, or the blackboard, and various client software or modules interact with the common repository. So in the data-centric style, a data store can be a file or a collection of file or a database, resides at the center of the architecture. And this database is then accessed frequently by other components that add, update, delete, or modify that data. Subsystem components or clients can exchange data in two different ways. First, shared data can be held in a central database or repository and may be accessed by all subsystems. Second, each subsystem maintains its own database and passes data explicitly to other subsystems through message passing mechanism. Of course, the second technique is more suitable if the amount of data that is to be shared is small. But for the large amount of data, having a common repository of data in the middle of the architecture is a suitable technique. The majority of systems that use large amount of data are organized around a shared database or repository. This model is therefore useful for applications where data is generated by one subsystem and used by other subsystems. Example of this type of architecture includes command and control system, management information system or database systems, CAD systems, and case tools. For a language processing system shown in this diagram is based on the data-centric approach. Of course, you don't need to understand how these components really work. The basic idea is that a very common language processing system is built around the architecture, what we've been calling the data-centric approach, where we have the common repository and different components get the data from that common repository. Dear students, the second design style is called a client-server architecture model. This model is suitable for distributed systems. The architecture design of the client-server model looks like as shown in this diagram. We have a number of clients and a number of servers. Clients and server interact with each other with the help of a communication media. The client-server model we just shown you has a number of client and a number of server software. The model has a number of servers which offer services to other subsystems, a set of clients that call on the services offered by the servers, and a network that allows the client to access these services. The clients are generally subsystems in their own right. Therefore, they should be designed accordingly. Similarly, a client is defined as a requester of services, and a server is defined as the provider of the services. Now, there is one misconception. When we use the word server, generally we think server means a hardware, a machine. But we should be clear that when we use the word server and client, we mean the software which provides specific services and the client software which accesses those services. Of course, a single machine can have both client and server software running on them, depending on the software configuration. An example of a client-server architecture design for a film and picture library system is shown in this diagram. So we have various client softwares, client 1, client 2, 3, and 4, and different server software might be running on the same machine or on different machines. The client sends the request to the servers with the help of a network, and the respective server then sends the reply back to the client software. Most internet services are examples of client-server applications, including the World Wide Web, FTP, Telnet, and Gopher. Oracle and many other software also use client-server architecture. For example, in Oracle, we have the Oracle database server running on a machine on which all the data resides, and a number of client software running on the workstations used by the users, and then they send the request to the database server, and the database server then sends the reply or the data required back to the user. The third important architecture design is called data flow architecture or pipe and filter model. This model is applied when input data are to be transformed through a series of computational components into output data, as shown in this diagram. So we have a number of filters, basically which are the data processors. Data processors are connected with each other with the help of pipes. So each filter receives some data, does some kind of processing, and produces the output, which becomes the input to the next filter in the sequence. Of course, the data produced by one filter may be input to more than one filters. When the data produced by one filter is used by only next filter in the sequence, then this type of data flow architecture is called batch sequential. Now this model is quite familiar to you, as we have discussed the data flow diagrams, basically which are the data structure diagrams, basically which follow the data flow architecture. An example of a system based on data flow architecture is shown in this diagram. So we have invoice processing system. There are a number of filters which are connected with the help of pipes. Now each filter receives some data. Now that data may come from some external entity. Then the filter does some kind of processing on the data, produces some output, which becomes the input to the next filter in the architecture. The next filter then processes some data which is received from the previous filter, and it might also receive some new data, and then produces the output which can be used by one or more than one filters in the sequence. And the last filter might produce some kind of output which goes to the user. Dear students, the fourth commonly used architecture style is called a layered architecture, in which a number of different layers, or we sometimes call the abstract machines, are defined. Now, each layer provides a set of services used by the layer above it, as shown in this diagram. So this is the layer architecture, where the software has been designed in layers, and each layer uses the services which are provided by the layer just under that layer. Of course, the name of the layers are not important here. You might have different layers depending on the application you are developing. The basic idea is that the software has been developed in a number of layers, where each layer provides some functionality and provides some kind of interface and services which are used by the layer above it. Perhaps the well-known example of this approach are the Unix operating system and OSI reference models, as shown in these diagrams. Here we have the Unix architecture. You can see it has been organized into a number of layers, where each layer provides some services to the layer just above it. Now, one thing must be remembered, that each layer provides the services to the layer above it through a well-defined interface. That means once this layer makes use of the services of the layer under it, then the layer makes calls using well-defined interfaces to the layer just below it. Similarly, the OSI reference model has been organized in a similar way, as shown in this diagram. So we have again 7 layers. which is the OSI reference model. Of course, different layers provide different functionality to the layers just above it. Then each layer uses the services of the layer below it by making well-defined calls to the layer below it. Dear students, the last architecture model we would like to mention is call and return model. A general call and return model is shown in this diagram. We have a main program and a number of routines or functions organized in a tree-like structure. Main program makes calls to routine 1, routine 2, and routine 3, and then the routine 1 makes calls to routine 1.1, routine 1.2, and so on. Now, the call and return model is, of course, the very commonly used architecture style we use when we write simple programs. When a module makes a call to the another module, we know that the module has to pass some information to the called module, and consequently, the called module might return some of the results back to the calling program. Now, there are two different ways in which this can be achieved. Either the calling program sends the parameters to the called program, and then the called program does the processing or performs the action and then might return some result back to the calling program. In a distributed fashion, a calling program might call a function which might be residing on a different machine. That's what we call the remote procedure calls. Both methods are used and they follow the call and return architecture model. Dear students, in today's program we discussed data design. We also discussed software architecture design and briefly touched upon some of the common architecture styles. In the next program, we'll talk about software testing, different techniques and methods which are used to test the software. Till then, Allah Hafiz. Dear students, Assalamu alaikum, and welcome to the 17th program on Software Engineering 1 course. We discussed in the last few programs about the techniques and methodologies that are very useful in user requirement gathering and designing a complete system that satisfies all the user requirements. Once the design is complete, coding can begin where physical design specifications are turned into working code by the programming team in a suitable software development environment. Depending on the size and complexity of the software, Programming can be an involved and intensive activity. Once the coding is begun, the testing process can begin and proceeds in parallel with the development. Testing is a very important activity of a software development process. And it is precisely this activity that we are going to discuss today. In today's program, we will discuss what is software testing process, and some testing techniques that are geared to discover program faults and errors. But before we define and discuss software testing itself, it is important to understand the difference between an error and a defect in software engineering. In software engineering, an error is defined as a flaw in software engineering work product or deliverable that is uncovered by software engineers before the system is delivered to the end users. A defect is a flaw that is discovered after delivery to the end user. Dear students, there are a few things that should be noted here. First, by error, we do not only mean that our code has some errors and fails to deliver some functionality as required by the users. But if the system does not satisfy the non-functional requirements, such as reliability, efficiency, it should also be treated as an error. The types of error which can result in failure of a software include omission of requirements. That means some of the requirements have not been implemented by the programmer or in the design. Incorrect specification, which might have been obtained during the analysis or the design phase, and they have been wrongly implemented. Then there might be errors in the high-level design. For example, our architectural design might not be the accurate design. The errors in the low-level design, such as the logical errors. Then your code may also have some errors. The errors might be syntax or semantic errors, which needs to be removed. Then user interface errors might also be there. That means you might be getting the wrong output or incorrect error messages. Then your system might not perform according to the specification. It might not exhibit the reliability and efficiency that is required by the user. Then there might be errors in the documentation you have prepared. Now you should remember here that by software we mean the program as well as the documentation which is prepared for that software. Then there might be errors in the module interface, and your program or software might not be properly handling the exceptions. Of course, there might be many other types of errors which you can come across while you are designing and implementing and testing the system. It should be a priority of a software developer to make sure that when the software is delivered to the user, it is error-free, which is a really very hard thing to achieve. Nevertheless, software engineers can try to minimize the number of errors in a delivered product. Software testing activity achieves just that. Formally, software testing can be defined as software testing is the process of exercising a program with the specific intent of finding errors in the software. So software testing is not about testing the code only as is generally believed. Rather, it is a much larger activity, as we'll see shortly. A comprehensive software testing should show us the errors in our programs, code, documentation. It should exhibit whether the software and related documentation conforms to the user requirement, it should exhibit whether our software performs according to the required reliability and efficiency criteria set by the user, and whether the software has adequate quality which is required by the user. We should remember that the purpose of software testing is to uncover errors, and therefore testing cannot show the absence of errors. It's very important to note that testing can only show that software errors are present. Therefore, a good software testing technique is that technique that has a high probability of finding as yet undiscovered error. Dear students, virtually all developers know the frustration of having software bugs reported by users. When this happens, developer inevitably asks a question: how did those bugs escape testing? Countless hours went into the careful testing of hundreds of thousands of variable and code statements. So how could a bug have eluded such vigilance? The answer requires first a closer look at software testing within the context of development and what testing techniques were used for a particular software. Second, it requires an understanding of the role of software developer and tester. So let's first look at who is responsible for testing the software and related documentation. Now, basically, there are two major parties which are responsible for testing the software: the developers themselves and independent testers. Now, of course, developer understands the system, but the problem with the testing done by the developer is that generally they do the testing very gently, and that testing too is driven by the delivery deadlines. Whereas an independent tester must first learn about the system and the functionalities required by it. But of course, he will attempt to break it, and he is driven by quality. So in a real environment, the testing has to be done both by the developers and by an independent team. Now, there are two approaches to software testing. In the first approach, we formally prove that the system is failure-proof. This is possible if we have a formal definition of all the components of the software and requirements. Now, this approach is not used much, though considerable research has been made and still done in this area. The second approach relies on performing certain tests designed to find errors in software, and no formal mathematical proof is provided. There are different techniques that can help develop appropriate tests. We'll focus on the second approach, and we'll discuss what tests should be performed and how they should be performed to test a software. But whatever approach you use for testing, testing generally begins at the component level, at the smallest level. You might remember that we discussed this thing before, that a system is made up of various components which are integrated and they work as a unit. So testing also starts at the component level and then works outwards toward the integration of the entire computer-based system. In a conventional software testing strategy, we start with unit testing and concentrate on each unit or module of the software as implemented in source code. Then we move to integration testing, where tested components are assembled or integrated to form a complete software, and the system as a whole is tested. Integration testing basically addresses the issue of verification and program construction. That is, making sure that the system has been developed according to the design and the components work together cleanly. After the software has been integrated, a set of high-level tests are conducted to make sure that the software does what the user really wanted it to do. That is, software satisfy the real user requirements. Validation testing provides a final assurance that a software meets all functional, behavioral, and performance requirements of the users. At this point, it is important to note that any testing strategy will fail if certain issues are not properly addressed. For example, for effectively employing a test strategy, one must state testing objective explicitly, understand the user of the software, and develop a profile for each user category, conduct formal technical reviews to assess the test strategy and test cases themselves. And above all, testing and test should be planned long before testing begins. Test planning can begin as soon as requirement modeling is complete. And test cases can be designed as soon as the design model has been solidified. So we have the wrong notion that testing basically is concerned only once the code has been developed, which is not true. Basically, we should do the testing and start doing the planning for the testing, that how different components will be tested while we are doing the analysis and the design of the software. Dear students, there are two complementary types of testings. So in static testing, we're concerned with analysis of the static system representation. That means the programs and the documentation to discover errors there. Whereas in dynamic testing, we concern ourselves with exercising and observing the behavior of the product. Both type of testing is important and has to be carried out. Static testing involves analysis of source text or the code by humans or by software. It can be carried out on any document produced as a part of software process. The objective is to discover errors early in this software process. It is usually more cost effective than testing for defects detection at the unit and module level. It also allows error detection to be combined with other quality checks. Static testing involves analysis of source code by humans or by a testing software. It can be carried out on any documents produced as a part of the software process. The objective of static testing is to discover error early in the software process. It is usually more cost effective than testing for defect detection at the unit and module level. It also allows error detection to be combined with other quality checks. Static testing is not only useful to test non-code elements of the software, such as documentation, but it has been shown to be very effective to discover certain type of errors in the code. Statistics show that more than 60% of program errors can be detected by informal program inspection. And more than 90% of program errors may be detectable using more formal program verification techniques, such as program inspections and structured walkthroughs. During static testing, we can discover certain types of error, such as data fault. The examples are, for example, the variable used before they are initialized in the program, variables declared in the program but they are never used, variable assigned twice but never used between assignments, which is a useless activity. You can also check for possible array bound violation by the programs, and you can also check the undeclared variables. With the help of static testing, we can check for the control fault, such as unreachable code. We can also check for input-output faults. For example, variable output twice with no intervening assignments. That value of the variable was printed twice, and the value of that variable did not change in the program execution. We can also test for interface faults between the modules. For example, we can check for parameter type mismatches from the calling program to the called program. We can also check for the parameter number mismatch. For example, if a function requires 3 parameters, you can check that you are passing the right number of parameters and the right type of parameters. You can also check for non-usage of the result of functions, that you make a call to a function, but the result returned by that function is not used. And you can also check for uncalled function and procedures which have been developed but not used. Another category of static testing check includes the storage management faults. For example, you can check for unassigned pointers and very common errors which happen in the pointer arithmetic. So you can see there is a long list of errors which can be checked with the static testing. But on the other hand, the objective of dynamic testing is to discover errors in running systems. That means we execute the program, provide some input to it, and then we see how the program behaves. In dynamic testing settings, we run the system or a component, provide it with some input, and observe the output to make sure that the system takes the correct input and provides the correct output. Also, dynamic testing is vital to test the conformance of the system to efficiency and reliability requirements, which generally not possible with static testing. The dynamic testing of a system can be done at various stages and level where you are developing the system. For example, we can do the unit testing, where each module which we develop is tested in isolation independently from the other modules to make sure that each module developed by us works as per requirement. Then we can perform the integration testing, in which a number of modules are integrated and they are tested to make sure that once these modules are integrated, they will work correctly according to the specification. We can also perform function testing to make sure that the system as a whole provides the functionalities required by the user. We can also perform the performance testing, making sure that the system provides the performance requirement to the user. We can also do the acceptance testing, in which the client is invited to test the software for acceptance. And generally, acceptance testing is done once the whole system has been developed. And acceptance testing is also called the alpha testing. Then, installation testing can also be carried out, in which we install the system on site and the software is testing again to make sure the software is going to work properly in the real working environment. Another kind of testing which is used is called the beta testing. In beta testing, the software is given to many customers for them to install and test with no test guidance at all. So you can see the testing can be done at different levels and might be done by different people. We have emphasized the point many a times that each software development process activity should be performed according to a suitable and well-defined process. This is also true for software testing activity. Testing should not be treated as a single and isolated activity. Rather, it consists of a number of smaller activities which need to be performed. A dynamic testing process generally consists of these steps. First, we design the test cases, and the result of this activity is test cases. Now, test case basically includes the input you will give to the system and the expected output that will be produced by the system. Then we prepare test data. Test data is basically only the inputs which will be given to the software to test it. So we get the test data. Once we have the test data, then we run the program with our test data, and of course we check the test, we get the test results. So the results which are obtained from the program, they are compared with the test cases, and then we prepare a test report which indicates whether our system has some errors or not. So test data is basically input of the system that is devised to test the system. Test data can sometimes be generated automatically. We have available many automatic testing software, whereas the test cases include inputs to test the system as well as the predicted output from these inputs. If the system operates according to the specification, test cases cannot be generated automatically since it is impossible to predict output. Dear students, there are two complementary approaches that are used for dynamic testing. They are generally known as white box testing and black box testing. We'll touch upon both of these techniques very briefly. In the white box testing, we basically test the code. So our goal is to make sure that all the statements and conditions have been executed at least once. So in white box testing, tests are conducted to ensure that all internal operations are performed according to the specification, and all internal components have been adequately exercised. In white box testing, you see, again, we can start with the component. We have the code of the component. From the code, we can derive test data. Then that test data can again be input to our program, and we can take the test output, and then we can compare our test output with the predicted output to make sure that the component works according to the specification. So in white box testing, we use the program code and requirement specification. A software engineer can drive test cases that guarantee that all independent parts within a module have been exercised at least once. These test cases can be used to test the component itself. We'll discuss different techniques which are used for white box testing in our next program. But on the other hand, in black box testing, we verify whether or not a system or a component provides all functional requirements. So black box test examines some fundamental aspects of a system with little regard to the internal logic structure of the software. That means in black box testing, we have the system which is treated as a black box, so the tester doesn't have to know what is the logic, what is the coding inside the system, and how the system works internally. We take some input test data, which can generally produce some errors in the software. Then we give that input to our system, and we get the output. Now, output can reveal the presence of defect. So, in the black box testing, the important thing is that the user can only see how the system takes the input and what outputs are produced. But how the system basically produces that output is invisible to the user. So we are not interested in the logic of the program. Now, black box tests are used to demonstrate that software functions are operational. That is, input is properly accepted by the software, output is correctly produced, and integrity of external information, such as data file, is maintained. The test cases are generally derived from system specification in the black box testing. Dear students, in today's program, we discussed what is software testing. Then we discussed the software testing process, and we briefly mentioned some testing techniques that are geared to discover program faults and errors. We'll continue our discussion on testing in the next program as well. But if you have some comments and suggestions about these programs, please do write us on the address given on your screen. So till the next program, Allah Hafiz.